set for the end of the course. So, okay, so let's conclude today with the general value integral, well, in the general case. So essentially, if you remember, so we started with something like how to integrate a function f defined in some bounded set. So let's say even an integral is okay, minus n into r, which is bounded and measurable. Okay, so the idea is that, well, you approximate f by simple function above and below, and essentially the measurability tells you that they the value, well, the simple functions are measurable and they converge. So f is either the sup phi less or equal than f, or the inf psi larger than f, and they are simple. For simple function, well, it's easy to compute what is the integral. Just the sum of the constant times the measure of the level sets. In that case, you have finitely many level sets to consider. Okay, so after that one, so the integral is good, it's linear, and well, we have the monotone, the background here, and we're going to see it now. So after that one, we want to give something better when f is not bounded. But when f is positive, for example, you don't care if the value is plus infinity. So you just require if f is in 0, well, we can say the integral of f is the sup of the integral of g bounded and the measure. Well, with bounded support. Actually, this bounded support, you see, is completely, you can replace with something like the measure of the support of f is less than plus infinity. Because it's only used here. Now you want to be sure that the integral of simple function, they do not have forms which cannot be decided, plus minus infinity. Plus infinity minus infinity. So it's just used here. And
why do we not want that?
Because it's not the same.
Sorry?
This is the value.
Oh, okay, wait, stop. Okay.
Just if you decide, you give a value, but then you break the addition and just.
It's just
just that.
Yeah, it's just like it's all different approach. You look at positive functions.
Yeah. Indeed, there is equivalent. In that case, you have only one value, plus infinity.
Yeah.
Indeed, here you can allow. Well, and then this is also the sup phi simple. And, okay, but you cannot take the inf of this guy. This can be plus infinity, even if the value is finite. Okay? So finally, how to get the general case? Well, we already did the other time. So if f, well, we need the definition because what we want to preserve. So let me write what is the integral of f. You expect this to be the integral of the positive part minus the integral of the negative part. And this guy is the max between 0 and f. And this guy is the max between 0 and minus f. You'd like to have something positive. So this is what you want to have, which is fine, but for the same situation as before. This is plus infinity and this is minus plus infinity, so you cannot decide. Okay, so actually, yes, you can say that I just accept function for which this one is plus infinity, and function or the opposite, but then when you multiply by a constant, you get the opposite case. and you want to preserve the linearity of the integral, no? You understand? It does that. So the only way is to ask that both are finite. And then you need to have a definition for this, because it's important. So f is integrable if, well, there are several things equivalent. So let's say the integral of f plus and the integral of f minus are less than plus infinity, and define this object. The integral of f is the difference of the two. So actually this is called L1. So f is in L1 is equivalent to say that f is which is equivalent to say that the integral of the modulus of f is less than plus infinity. Why? The last one is almost clear.
Oh, because
this guy is the integral of f plus the integral of f minus.
fine.
Minus. Plus, yeah.
Minus.
Yes.
No, sorry, that's b.
Plus, it's plus.
Plus the box.
F minus is positive. It's by convention. It's not. It's the negative part. So the negative part of minus 3.
Measurable functions. And,
Both of the integrals exist.
Because always is in the 0. And then this guy is certainly positive, and then it is measurable and positive, so I can also compute this. If it is finite, then it's finite. And these are equal because the linearity holds for positive constant for we saw last time. So the integral of f plus g, if both are positive, the sum of the integrals. So if you give me f, I take the modulus, which is equal to the sum of these two functions. Okay. So I can either compute the integral here or compute two integrals. The value is the same. So requiring is less than plus infinity, requiring the sum is less than plus infinity is equal to requiring that both are less than plus infinity. You understand? So your question was why is this defined? So let me repeat. Give me f. This is positive. So I can compute the integral, no? Okay. This is equal to this sum by definition, no? And the integral here is linear. Well, it's positively linear. So this is equal to this sum. Requiring this sum is less than plus infinity means that both are less than plus infinity. So I'm going back to the definition. And so actually I'm not computing, so I'm computing these two, the sum of these two, or the difference, not really computing. In the theory, you just compute essentially the integral of positive functions. Indeed, sometimes it's presented like this. Actually, usually maybe shorter, but okay, it's fine. Okay, so finally we have a way to give a number to this symbol, which I called this symbol, which is called the integral. That's it. Now we are in the general case. Okay, let's see some stupid exercise. If f is less or equal than g, and the integral of g is less than plus infinity, then f is in L1. Okay, it's clearly obvious. The problem is to show what, which property here. Okay, yes. And then I use the monotonicity here. Now for positive function, I show that it is monotone. Integral of modulus of f less or equal than integral of f. Yeah, it's obvious. Why? But why? And because I can only use the
Because
definition.
if we take the modulus here, we use the triangle inequality
Yeah,
and
exactly.
apply this condition.
Yeah, is the triangle inequality applied to the definition. Okay, so let's go on with something which is still obvious. So, F, G are in L1, and F less or equal than G, then the integral of F less or equal than integral of G. I need only the definition.
Yes, because we just write yes, this.
And the F minus is, remember, because I changed sign. Okay? So I have the integral of F plus minus integral of F minus. This is less or equal than integral of G plus, and this is less or equal, minus this is less or equal than minus the integral of G minus. And A in R. Okay. But this is
It's a bit longer. We have to look if I is positive.
yeah, if it is positive, I just A, otherwise they exchange. No? So it's positive. So. And finally, but what is missing now? I'm trying the monotonicity and linearity is missing just integral of F plus G, no? So. So here I'm a little bit in trouble because I may have F plus minus G minus. And so which is the sign of this one is not clear. So I'll just give you, so use. Well, there are several proofs, clearly. You can, for example, you can just split into several parts. When one is larger, one is lower, and then you see that they, or in the book there is a nice trick. So let's say F plus G plus F plus G minus is equal to F plus minus F minus plus G plus minus G minus. Which is, well, it seems like a joke, no? But actually it just tells you that when you are F plus, only one is different than zero.
Tells what?
Only one is different than zero. And actually, because this one is F plus G and this one is F plus G. So they coincide by definition, because it's just, I'm just rewriting. Okay, so now I just write. What I do, I want something positive. Okay? So I arrive with this equivalence. And now we integrate. Yeah, it's a fast trick. So this means that F plus G plus F minus plus G minus is equal to the integral F plus G minus plus F plus G plus. And now everything is positive, and for positive function I have already that it is linear, it is additive. So, well, just okay, and then if you rearrange, you obtain exactly the integral of this guy is equal to the integral of this guy plus the integral of this guy, which is what you want. But there are other proofs. For example, okay, well, we will see later. So, because we have the Lebesgue uniform convergent theorem. So, another proof is the following. So, F plus G okay. So, if I have linearity for some function which converges, and then I'm fine. And
In what level?
I want to use the following theorem. We are going to see it now. So the theorem is something like, so suppose that Fn converges to F, and Fn is less or equal than G in L1, then integral of Fn converges to the integral of F. So at this point, I have that if I take approximations, which are bounded by, for example, I remove a small set which is, so I take Fn with compass support and they are bounded. Essentially, I can approximate the integral here and the integral of both. So I have a uniform bounded, the function g here will be the sum of the two. And then for functions which are bounded with support which is finite measure, I'm fine. So this is a personal exercise actually. So how to prove it without using this trick. Okay, indeed the next theorem is exactly to prove this statement. Non-uniform bounded theory. Usually it's called the convergent theorem. Okay. So if you remember, we have the theorem where the functions are bounded. So now instead we have Fn, which are, they converge to F almost everywhere. And let's say Fn is less or equal than G, and G is integral. So I'm replacing the boundedness with just the integrability. And this is uniform integrability. Because I'm saying that the module is controlled by a function which is L1. So for all n, this is the uniformity. Then the integral of Fn converges to the integral of F. So very mild assumption. And I'm not taking even something which is bound. Okay? So even here there are several possibilities. So because now we have a lot of instruments, essentially we know that all the tricks, if you go back, well, you can use other advanced lemmas like we are going to do now. But if you want to go back, essentially the trick is always one. You approximate this Fn with something which is bounded and with finite support. It measures with finite support. That is always the trick. And then you can take also this thing continuous. And these uniform controls tells you that essentially what you are throwing out is more uniformly in n. Because this gives you a control. It tells you that, well, if I take something which is very large, so for example, the interval which is minus n, so I think this is more important than the proof. I'm sorry, I prefer to make a digression here because it's more important, and actually it's the heart of the matter. So the heart of the matter of all these theorems, why you need G in L1 or other some weaker conditions. Because all these theorems are fine whenever you are in C0 and uniform convergence. Everything is trivial. So the only thing is that you have to prove that by doing this approximation, you are not losing something which can become, which is not small. Okay? So for example, here, I can invent the following proof. Okay, so let's say I know the theorem holds when something is bounded as a support and also as F, because then I use Egorov. You see, I'm coming back. So I need to prove that this is fine whenever I replace my assumptions with something which is weaker. Understand the point? The point is I'm always going back at the bottom. So for example, I want to show that the integral for x greater or equal than n and then k of fn is less than epsilon if k is sufficiently large and for all n. So this is uniform in n. Well, I'm fine, because exactly what is written here. This is less or equal than the integral of g when x is less or greater than k. And now g is integrable. So I know that, well, this is going to 0 because otherwise I have some trouble. I know that, for example, the integral of, let's say, some ei of g tends to 0 if ei is a family of set which converges to 0. Because, okay, I have to work a little bit here. But you can think that if this is bounded, essentially this is, and then in every piece, so I break R into a sum of intervals, I know that the sum holds, and I'm saying that essentially the sum of this guy converges to the integral. Because remember, it's the supremum of function which has bounded support, which means that the tail should go to 0. Okay? So here what I'm using is that the integral of g is the limit over n, the integral from minus n, the limit over k, the limit minus k to k, g. This is by definition of the integral. G is positive, it's the supremum of something which is below g with finite support and bounded. And since this is less than plus infinity, this guy should converge. Because otherwise the integral is plus infinity. Okay, so you see, I proved that essentially when I computed this limit, if I can make an arbitrarily small error, and then I'm reducing to something which is bounded. And the same for which has bounded support. The same for Fn, which is bounded. So the fact that it's controlled by G means that the set where Fn is uniformly large. So if Fn is larger than K, this set is contained in the set where G is larger than K. And now I have the uniform estimate. This is small, simply for the same reason like this one. The integral of G in the set where is less than or equal than K should converge. You see, we are not going to use this proof, but always, I think this is really the heart of the matter. You always reduce to the principle you know. And the principle are that, well, you want to go back essentially, well, I am pretty fine every time the measure is finite and F is finite. Why? Because I know that if F is, in that case, I have very strong results. So continuous function, Egorov theorem, open sets. So all the assumptions that you're going to put, I'm not saying that every time you have to reduce the proof, because here the proof is long. It can be quite long, because essentially I'm reconstructing all the theory starting from the definitions. But you have to keep in mind that it's always like that. So you should always can reduce to the bottom. You don't know how to do the proof, you do to the bottom. The bottom is always that essentially we're working with uniform convergence and continuous functions. Whenever you can use that setting, you're fine. If not, well, maybe the result is false. So indeed, the proof here is much faster because you can use some theorem which is still based on a theorem like this one. So observe that G plus or minus Fn is greater than 0 because it's written there, no? Okay, so Fatu, and then I use a big tool which is Fatu level. So the integral of the lim inf G plus or minus Fn is less or equal than the lim inf G plus or minus Fn. Okay? So now this converges. So this guy is the integral of G plus F, which is equal by linearity G plus the integral of F. Because I'm using the linearity here, which is fine, because clearly F is less or equal than G, so it is linear one. And here I have the lim inf. So again, this is the integral of G plus or minus the integral of Fn. So the integral of G exits the lim because it's just constant.
So
Yeah.
you can get rid of the plus minus and put just
Oh,
plus.
sorry, just a mistake. I forgot. It's always because then I need to change some. So for the plus, I need I'll take F less or equal than lim inf Fn. For the minus, well, it should be minus F less or equal than the lim inf minus F, so minus the lim inf of Fn, which is equal to minus, well, you revert it, the lim sub. So I obtain that the integral of F is greater or equal than lim sub. But and now you see, it means that they coincide. The lim inf is certainly less or equal than the lim sub. On the other hand, it's larger or equal than the lim sub. So they coincide, the limit exists, and it coincides with F. It's much faster. Much faster because I'm using a big gun, which is a Fatu. Otherwise, I have to reconstruct everything. So let's see some nice exercise here about this thing. I really hope what it enters in your feeling is that, yes, I can have short proofs, but even if I don't have short proof, it's more important that I feel that I can go back. And then I'm fine. Suppose F1 or R, which means that, well, we always assume R. Then the sum from n equal to 1 to plus infinity of the integral of f from n plus 1 converges. Any idea?
Yes.
It's already there. Oh, yeah, it's written in the theorem.
Okay. Fn.
Yeah. Because the partial sum is the integral from 1 to n, which is equal to the integral from 1 to n and 1 from R, the indicator function of 1, we don't, well, n, closed or open, doesn't matter, it's got to measure 0. And so I can apply the theorem. This, if you call this guy f tilde n, then f tilde n converge to f, and f tilde n less or equal to n. So it is linear 1. Is the opposite true? So take f. So let's say minus 1 over n for minus 1 to the n over n if x is in n plus 1. Okay, so let's see. So this sum becomes the sum now the sum converges, but not absolutely. It converges. So essentially, if you go, well, any criteria you want to use, but at the end, just take the difference between the two terms, less or equal than the next step. So one way. Okay, so however, well, this is positive, so I just can, is the limit for the sum up to n, so it is the sum, and now, okay, so it means the following. That you cannot imagine to, so the convergence of the series is in the sense of the absolute convergence, but not in the sense of the standard convergence, because the integral requires an absolute value inside. So it's different from the generalized Riemann integrals, because this guy over here could be thought as a generalized Riemann integral. So you integrate up to n and you take the limit. But for Lebesgue, you cannot. Because Lebesgue has no, because here you are using the ordering in R. I take up to n, and then I can go to the next one up to plus infinity, which is like for the Riemann integral when you take step function. You take the ordering in R. However, for the Lebesgue theory, you forget the ordering. You just take counter image of level sets and they are just subsets. So there is no way to match this limit. However, you can still define an operator which is the limit, so give me an f, and then define the value whenever it exists as the limit of 0 to plus, of the limit as n to go to plus infinity from the interval from 0 to n. That's fine, but it's not the, well, it's not the integral. It's another operator. The integral is an operator, and then you have another operator, which is a pure definition. It is just, I don't know. This is something stupid. This is something stupid. This is stupid too. this exercise. So it's Fn. So let's say Fn converge to F almost everywhere, and F is in L1. Then the integral of Fn minus F tends to 0 is equivalent to implies integral of Fn converges to the integral of F, because I think that there is a mistake. So this is something I wanted to do because I look at the text and then I suppose there is something which is not working, because the text says to prove the opposite, that they are equivalent. Okay, so let's see. I think it's false. So let's prove one direction. This implies the convergence of the integrals. And we can take even Fn in L1. Okay, so you can write, well, the integral of Fn is equal to the integral of F minus Fn minus F plus F, and this is less or equal than the integral of Fn minus F plus the integral of F. On the other hand, is larger or equal than the integral of Fn minus Fn minus F plus the integral of F. Okay, so it means that they converge. So this is fine. So let's find a counterexample, because I believe it's false. So I can also, so if the integral converges, the value, but they do not converge. So even if the integral is converging, but actually they do not converge. I think the exercise will just verify whether these two conditions are equivalent. So let's start in R. There are two ways to have troubles. No? One is that the mass goes to plus infinity. You remember, this was the same trouble whenever you have to prove that the sets are shrinking to 0, but the measure is
We
not.
take these functions.
And then the integral is plus infinity.
What?
The integral is plus infinity. I want to have something which is not.
Yeah, you just take it
Maybe
up
that
till 1
example
to
you
1.
are saying.
Its value is 1 until n, and then it becomes 0.
Yes, or it becomes 1 after n and 0 before,
Yeah.
like there.
So it will converge to the constant function 1?
Yeah.
The other way.
I don't know.
The other way. You make it 1 outside of some interval.
Yeah. Then
Then
it's
it
plus
converges to
infinity.
0.
But the integral is plus infinity. It converges to 0, but this is always plus infinity, and this is, you know that this is finite, no?
Yeah. You take the 1 minus the characteristic function of some interval.
Yeah, let's start with something, simplify the problem. So let's take something like Fn minus F is equal to Gn. Then we have that the integral of Gn converges to 0. Okay? So no, what I have now, I have that, okay, this guy.
So if we
So I have that Fn is equal to F plus Gn. And I know that the integral of the modulus of n converges to the integral of the modulus of f, so which means that the integral of f plus Gn converges to the integral of f. And I suspect because
Both are L1 and F.
both are L1, yeah. But actually, if you need only yeah, both are L1. I suspect because I don't see now the trick. There is a trick here. Gn converges to 0, and the thing converges. Let's see. You see, sometimes I cannot get it. Because I cannot move this plus infinity.
what's the problem with this exam? If we take a small interval around the origin, and this interval increases in size,
Yeah.
and this interval is 0 and the function is 1 elsewhere.
Yeah, but then the integral is plus infinity, you know?
Yeah, the integral is plus infinity.
Then it is not converging to something finite.
We're proving that.
Yeah, that's the problem is that otherwise it's fine, no? So
The Chebyshev inequality doesn't work to prove it. Because we compute the difference.
okay. Yeah, so Chebyshev says that essentially the set where because you have this G, no? So you know that G.
Okay.
Then you see how to use that.
No, because below.
I think will come up. Okay, because one is fine, it's the other that I have to think. For some reason, I don't see now the proof. Or the counter example. I believe now it's correct. Because the trick that you can use, they don't let this convergence to hold. So if I want this to be not going to 0, then I don't get that this implies that that cannot converge. It's fine.
Can we take a constant function Pn equal to minus p?
2 minus?
Minus p.
What is p? Minus 5.
Function every point equal to this function minus p. The model is equal to this function. Sequence is constant functions. It's not constant. All term of sequence is functions. Sequence is equal to phi or minus p. Oh, minus f. This. Oh, yeah, it is minus f.
Yeah, but then this is not going to 0, no?
Yes, of course. If f is not.
This is not converging.
Oh, this also.
Yeah, this is converging.
Context of maybe.
Ah, okay, yes, yes, I see. Yes, yes. Okay, so the function is as usual, 1 over n I higher n. But it's not going to 1. No, because it's false. This is not converging.
Sorry.
So I believe it's true.
So the integral on the left hand side is we can approximate it by both integrals on the right side.
With the difference. Is it also even that the sum?
The sum, yeah.
Yeah.
And both integrals on the left converge.
But the sum, it gives that is equal to sum constant. No, I think it's true, but actually, let me see. It's definitely true. No, okay, it's false. Yes, because the problem is the 0 which breaks the stuff. But then I take something which is like this. N minus n, 1 over n, 1 over 2 over, so 1 over n. The integral of n is equal to 0. No, the modulus, yes, because, yeah, wait, now I see the proof. I think I see, because this guy, I have a modulus here. So, because, you see, if I'm inclined to, I mean, the previous exercise, it's true that the integral is 0, but not the modulus of the integral. Okay, so let's see. If I take something, so this is f. So let me see. Let me say f greater than. So yeah, I can take f plus because I have this guy. So when f is larger, I'm coming. So let's see. If I take fn equal to, so I take gn is equal to fn when f minus f. So the integral of fn minus f is equal to the integral where fn minus f is positive, use the plus gn, plus the integral where plus fn minus f negative. So this tends to 0, so it means that the integral of fn minus f positive and the integral of fn minus f negative. I have only this guy, because the other goes to 0. It's bounded by a function L1. And now let's compute this object here. The integral of fn is the integral of, well, fn minus f, again, because I can use this guy, positive, plus what I have now, I have f. So when I take when f is larger, I use this fact, and then when it's lower, I use the other fact, and then I have only the rest. This is the rest, is when fn is inside. Okay, so this is less soluble than the integral of f, but this integral converges, because here I can use Lebesgue. This was a difficult one. Okay, so these two integrals, they go to 0. So the reasoning is this one. If I give you Fn, I just in this part, so it's controlled by F. I can use the monotonicity, the Lebesgue theorem. The only part which I need to control is this integral outside. But this statement, okay, so inside the integral converges. So essentially it tells me that the part which is outside the graph of f goes to 0. But the part which is outside the graph of f is exactly the part that here is not converging, because this is the part inside the graph of f. So f, and then you take minus f here. The part which lives inside is fine. The part which lives outside is only when it's larger or lower. But the larger or lower part is exactly the limit of this guy over here. So the difference between, so the part inside is converging. And so that these two limits, it goes to 0. So the result is 3. That's fine. I think there's a sharper proof. I see now just only this one. Okay, so another exercise. This one was a little bit tough. I think this is something smarter, but I don't see it now. Now let's take an f which depends on two variables, and assume that the following: for all y, f as a function of x, okay, is in L1. Actually, a little bit, yes. And let's say for all x, okay, actually it is really that. Let's say that f of x, y is bounded by a function g which is based only on x. So uniformly bounded in y. And now for all x, y goes to f of x, y is continuous. Prove that y, the integral from 0 to 1 f of x, y, dy, dx, which is fine because I have for all y, this object is an L1 function that actually is uniformly bounded, is continuous. Any idea here?
We can take a sequence that for each y, we can take a sequence y plus h. F of x.
So let's compute. So I need to prove the limit of this guy. So let's call this function. So take any sequence, let's say this is hn. Let's say the function gn, which depends only on x, because I fix y. And now what I have, I then, well, from this guy is less or equal than 2gx. Okay, so the uniform convergence, the Lebesgue theorem, tells you that this limit is equal to 0. Okay? So addendum f of xy, so y maps to f of xy is C1 and dy f of x, y less or equal than gx. Then y integral of f of x, y dx is C1. Okay, so I'm essentially saying I have a uniform integrability in x, and in y I have some regularity, which can be C0 or C1. And always I assume that whatever I'm going to compute is bound. So there is an observation. So let's do the same. Well, you write down what you want to compute. Is the limit, well, we forget the limit. The thing is that f x y plus h minus f of x divided by h. So this, for any sequence n, this would be the function gn. And I want to say this is less or equal than, well, a constant would be 2, or no, would be g in this case, then g. Is that true?
Sorry, what's the integral
Of the incremental ratio. I want to compute that is g1.
what is f of x?
Sorry?
Well, f of x and y plus
hn.
X is fx minus x y.
minus
Second.
No, it's just you forget to put down.
Yeah. Okay, why is that so? Let's fix x, and I compute this difference here. This implies, so the function is C1 and the derivative is bounded, so it implies what? Implies that f the integral of the derivative, which is g times h. Is exactly written here. The partial derivative, so the derivative along direction y, x is fixed, is controlled by g. It means that the difference is controlled by g times the length. So that's true. So I pass to the limit. Because this converts to the derivative. It converts to the derivative of f. Here converts to the integral, the derivative of f, x, y, and integrated in x. And now, so I just proved that it is differentiable. Why is that? Is this continuous? Is the previous point?
what?
Why it is continuous? Just prove that it is differentiable here, no?
Yeah.
So now it's not C1. C1 means the derivative is also continuous. You can have derivative, but not continuous. So why is that so? Simply because I can use the previous point. Again, I'm in the setting, so that this integral, this is bounded by g. So I can use the previous point. Okay, so let's go on with some other statements. So these are just exercises. A family I is disjoint, I'll measure the disjoint, then for all f in L1, the integral of f in the union is the sum of the integral of f. How to do that? Because now we have a very strong convergence theorem.
Take Fn
Change
equal
this. Fn is
the union over some point.
And is f union up to 1 of e. Okay.
and it's less than f.
Yeah, so Fn is less or equal than f and use the f. So this is an important statement. So it is countably additive, like a measure. Indeed, as a remark, it's not, we'll see later, for if f is in L1, then let's call this measure mu f of a set A is equal to the integral over A of f, say greater or equal than 0, in the x is a measure.
We can show this now, right? We can show this now.
This we can show that is
Oh,
true.
we already have the tools.
We have, yeah, this is one part, and then if A is the empty set, that's integral 0. The measure, moreover, we have that the measure of R is less than plus infinity.
Sorry?
The measure of the whole set is bounded because I'm showing this.
Oh. There is a partial converse, right? Every measure is an integral.
Cerrado.
No?
Limitado.
A partial converse under some condition.
We will see that here. But actually, you just count how many measures you can have and how many L1 function you have. They don't match. Too many measures and too few functions.
Oh, the measure.
You have many more measures than L1 functions. Now let's say the following. EI are in L and EI are decreasing to E. Then for all F in L1, the F in EI converges to F. Why is not the case for the, you remember, for the monotone convergence, or essentially when we did for a measure?
Sorry?
For a measure, recall, then the measure if
The measure is bound.
at least one is finite measure. Let's say just the first. So this assumption is missing here. Why? You have
Because it's in L1, so the integral one of them, all of them.
I'm restating the statement for this measure. But actually, I don't need anything because the measure is bounded. Okay? So just use, and the proof is the same. Because we have the countable union is fine, so we take the complement. Now the measure, so let's say, and now I can use that. now it's fine. Because I'm not having plus infinity minus infinity here. Then this one converges. Because R minus EI is increasing to R minus E. And then this guy converges. Okay. So another important notion, I think it's almost done. So you see, these are statements, but actually we can do exercises now. Is the uniform integrability. Okay, so let's understand why is this notion appearing. So let's take this example. Fn is equal to n in the set 0, 1 over n. This is a family of functions, no? Let's say like this one. So I don't have it. In L1. Fn is converging actually to 0 for any x. The value at some point is 0. But integral from 0, 1 of Fn is equal to 1. So it means that the mass is escaping.
So what?
Escaping.
What is escaping?
The mass, I mean the area. So essentially, Fn, that is positive, the integral is the area here. But in the limit, so the area is constant, equal to 1. Well, this is not that example, it's something else. But so at the end, I'm missing something, which means some part is escaping. And the only way to make it to escape is going to plus infinity. So one idea is that the mass is escaping to plus infinity like this guy. Another idea goes to plus infinity in that direction. That's why you can mix the two, but essentially you have only two paths. So here the mass is escaping to plus infinity vertically. So the other case is that Fn is the integral, let's say Gn is the indicator function n plus 1, and this guy, the mass, escapes horizontally. Okay, so these are the two mechanisms. We want to prevent these two mechanisms. Example. So example. If Fn is less or equal than G in L1, then this cannot occur. Why? Essentially, I cannot pump too much mass going to plus infinity here or too much mass going to plus infinity there. Why?
Because at some point the integral will converge to 0, and at some point the
If I count.
the bounded part.
You see, no?
Yes, G minus n is
Because this guy implies that essentially You see, no?
G has.
This tends to 0. So it means that I cannot pump the mass there. At some point, essentially, it's something like that. I shrinking my pipe, and at some point the pipe goes to 0. So I cannot pump. So, but the same from up going up, no? Because so Fn larger than K is less or equal than the integral of G and G larger than K, and this tends to 0. I cannot pump the mass. So now we want to, instead of having, well, the question is the following. Is the fact that I have a uniform control in L1, like in the Lebesgue theorem, necessary? So what I prove here, it is sufficient. Is it necessary?
Probably.
It's close to the change, you know?
But with
It's like the
Egorov,
change of inequality.
but with Egorov, we can say something that in the limit, the function is always.
If you have the uniform integrability, the uniform control on this escape, yeah, indeed the use is exactly that one. But I think you are going on. If you control the escape here, then you live in a context, then you can use Egorov, yes. But it's not necessary that it is a one. So because you see that uniform integrability requires only that this guy goes to 0. So this is K, because it's K here. This goes to 0 uniformly in N. No? So it's not required that you have a function. The function maybe is not even integrable because we know that this not only goes to 0, but actually in some absolute sense it converges to 0. So for example, I can say, so for example, if I take a series which, so let me say, let's write the condition, then fit. So the condition is that is escape to possibility vertically means that the interval where Fn is larger than K in some bounded interval, let's say, intersection bounded interval, so let's say AB, bounded, because I'm only considering bounded set of Fn goes to 0 uniformly in N. So the meaning of this uniform here is nothing more. Is that for all epsilon there exists K with the value of psi such that for all N the integral, let's say from A to B of Fn restricted to the set where Fn is larger than K is less than epsilon. This is the uniformity. For N fixed, I can choose epsilon, but I can choose epsilon which holds for all N. Okay? So I'm not requiring that this should hold. For example, I can take a function. So for example, I take a function, say 1 over the square root of x, and then I translate. So essentially, the function g should be plus infinity everywhere. But actually, clearly, this statement holds because it's just the translation of the same function. Understand? So the idea that you have this control in Lebesgue theorem is something that has hidden the idea that you can control uniformly the set where the function is large. So now let's do the other. The idea that, well, say the control, it means that I control essentially how much mass I have in the tails. Well, even there, I don't need that it is a 1. What I need is that for all epsilon, there exists, let's say here, n such that for all n, the integral for x larger than n of f small n is less than epsilon. N depends on epsilon. This is exactly what I need. I control how much mass I can push to plus infinity. And here it tells you that, well, if you're very far, you cannot push too much mass. So at the end, no mass is escaping. Okay, so you see the difference in the condition is the following. Is that for G, essentially, if the function is in L1, I have that this is controlled by an L1 function, and then I can split, you remember the example, I can split into pieces. And the function, the sum, the absolute value of the sum of the pieces is bound. While here, the epsilon is just something which goes to 0. It does not need to be a function which is integral. So, for example, if I take, let's say, a function which goes to 0 but 1 over x. So if I have fn less than 1 over x, this clearly is 1 over x. This clearly is a function which is fine from the point of view of the uniform, of the uniform integrability, which is, here is another name of this condition. But clearly is not fine from the point of view of being in L1. Because it's strong, this requires really that quantity is integrable. The assumption requires that this is. So now we can give the two definitions.
Can we not always find such a function?
G?
Yeah?
No, this is the example. So Fn 1 over x, the indicator function 1 over 1 to n. And okay, let's see, not 1 to n, let's see n plus 1. So it's even easier. The integral of Fn is bounded. Actually it goes to 0. But the only function g which is over all of them is 1 over x, and then you're in trouble. Okay, so after this example, let's do the definition. So here, let's change a little bit the type. Typings. Because I put two arguments together, but in my opinion, they are the same. So let's see. I put it here. So the idea of this section is that I want to relax the assumptions on the Lebesgue theorem and extract exactly what is needed for Lebesgue theorem. F contained in L0, or let's say L1, is uniformly integrable, and the other thing is tight. Okay. This refers to the first part. If for all epsilon there exists a delta, so now you remember, you see, when I say that essentially this is bounded, essentially I'm saying if the set is sufficiently small, the measure is uniformly small. We've showed that is equivalent for bounded set. So actually I want to enlarge a little bit this idea. So Here it means that if I take, for example, if the integral is bounded by Chebyshev, this set is small. The measure is small uniformly. And then I'm rewriting this idea. So if the measure of the set is very small, the integral of all functions is that set is small. So for all a measure of A is less than delta, the integral of Fn over A is less than epsilon. So the statement is no matter which is f, if the set is sufficiently small, the integral is small. And this is the opposite of the example. No? The example, you concentrate the mass in a set which has smaller and smaller measure. The example was 1 over n a n. And that clearly you left the mass to escape. We are going to prove that essentially is this guy here. So the thing is that you cannot let the mass to escape, because the mass escaping plus infinity implies that the support, the set where it is base is very small, because f is very large, and then I cannot push epsilon mass. So tight is the second condition. I do not let the mass to escape to plus infinity along the horizontal direction. So if, let's say, for all epsilon, and here, okay, here I want to give the tightness, the definition of tightness in the general case. Because even this one here, I don't see R. If I say minus larger than n, I'm using R. So let's say there exists a compact set such that,
Excuse me, but in the definition of uniformly integrable, we don't have these functions f and we only have a function f.
sorry, F. You're right. So now is the complement of the compact set is less than epsilon for all f in the family. So essentially the mass is uniformly contained in some large compact set. And then you recognize that why these are the two things that will make the job. Because this essentially tells you what you can just leave in compact sets. So I'm very happy, ego. And then I want to use bounded. Because for essentially, if you remember, there is always for bounded and compact set. And the boundaries, I'm recovering the boundaries from the first condition. Okay? So I think we have basically done. And what is missing is just the theorem. I can state it now, or
Excuse me, there is no constraint on the measure of k epsilon?
K epsilon is finite measure, but
Yeah.
this is going becoming larger and larger, and you don't need it. It's becoming larger and larger, but there's
K
no
epsilon becomes larger and larger.
Yeah. If you have the boundedness like f less than g uniformly, then you can get an estimate of k epsilon using g. But otherwise, you just know that this object becomes larger. You don't know how it's large. The important thing is that it's finite.
But you just say for every epsilon such a set exists.
Yeah.
It could be that this set is very small, therefore the complement.
Then it's better.
Sorry, it could be okay. It could be very big. So the complement is very small, and now the
And the
mass
problem is that
concentrates.
the complement is very small in which sense? So for example, if the measure is finite, well, and you know that they have a uniform integral, so first, I don't see what is the problem that is very
The
large.
problem is, you say there exists a k epsilon such that this happens, but
Yeah.
if k epsilon is very big, then the complement is very.
Very small in which sense?
Okay, it could be that k epsilon is all the real lines except a small interval.
No, because it's compact.
Okay. Okay.
Important thing is, sorry, I always forget because I say that I'm right.
Okay, sorry.
But the important thing is that it's compact,
Yeah, okay.
so it's a small set.
Yes.
From the point of view of R.
Yes. I was just missing this.
Yeah,
one.
no, it's my fault. I should have said, but then I did not write. But if, for example, if you are in, if you know that you're in a bounded interval, then this condition is implied by that guy. Exactly what you said. If a bounded interval, well, a compact set can leave a very little space. And then I can use the first condition to say that in that space I don't have too much mass. So really, this is something that you need only for when the space is large, for example, R. So you want to control the large part of the set. And this one just tells you that if the set is small, that is more clearly. Let's see why the two conditions they are complementary. So for example, you can take f is equal to the indicator function minus n. This is clearly uniformly integral. And the epsilon here is equal to the delta. But it's not tight. For any compact set, at some point the function becomes too large. And then the fn equal to...
Sorry, but the function eventually becomes 0, right?
No, it's just 1, always 1. But you can make it 0, for example, 1 over square root of n, it's the same. But it's not that problem. The problem is that you have too much mass.
Yeah.
And this is the opposite. This is clearly tight simply because it lives in a compact set 0, 1. But it's not uniformly integral because the mass is concentrated around 0. And so for every small neighborhood of 0, at some point the mass inside is 1. So it cannot be small. So we conclude the integral tomorrow and with the general Vitali convergence theory, which is a nice exercise. I mean, it's just, again, I want to replace the Fn bounded by G in L1 with Fn tight and Fn uniformly integral. And you will see that it's always the same. I just use the two parts. This one says that I live in a compact, and this one says that I live in bounded. Then we pass to the limit. It's always the same. Okay, so see you tomorrow. These are the key points.
By the way, I wanted to ask a question. In the first lecture, in the very first lecture, you mentioned that theory of integration is more or less independent from the theory of measure.
Could be.
Could be. But this is not carried out, or it is standard thing?
Because well, there are other definitions of integrals that are based on directly define the integral, and then clearly you define what is the measure by what using characteristic functions. I'm not an expert at why I never used it because essentially here one of the good things is that you have always the possibility to say almost everywhere or up to small set. And this is a part of the theory which, well, maybe you can do on the other cases, but this is really the power. And then you have this convergence theory, which are very strong. At the end, it seems very natural, like reading the real number from Q. So Q is just you measure finitely many intervals and then pass to the limit. And it's very close. This is my personal feeling. There are other theories, but at the end, the mainstream is always to give them the dimension. Yeah, I renounce to do the second half of the. I'm done.
Bye.
Bye.
I hope to finish by I hope to finish by next week. No, we can do two
Section of exercises.